Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's our pleasure to host Nati Srebro today from TTI in Chicago. Nati earned his PhD at MIT. After that, he spent some time as a visiting researcher both at the University of Toronto and after that at IBM Research in Israel, in the Haifa labs. And now he's a professor at Toyota Technological Institute in Chicago. And he's going to talk to us about his work, which won the Best Paper Award at ICML this year. So it's guaranteed to be, enjoyable for everyone.
Thank you. Okay. Hello. So what I'll be talking about today is actually two different things. I'll mostly be talking about training support vector machines. I'm going to explain exactly what specifically I'm going to what support vector machines are in particular in a bit. So I'm going to be mostly talking about training support vector machines, and then probably the last maybe quarter of the talk, maybe a bit less, also talking about clustering. And both of these, I think, illuminate fairly different aspects of an underlying theme, which I find is a very interesting and important theme, and I'll return to it at the end, which is looking at the interaction between computation and data, and in particular seeing how computation becomes easier as we have more and more data. And I just want to point out this is based on several pieces of work, mostly mostly with Shai Shalev-Shwartz, and also with Yoram Singer, and previous work with Shakhnarovich and Sam Roweis. Okay, so I'll start with the support vector machines. Just a quick reminder, I'm assuming that most of you here have seen SVM in some form or another. From my perspective, really SVM is just linear separation. We have a bunch of training data points, and based on these training data points, we want to be able to make future predictions where the future point is green or red, and we do that by finding a linear separator, but not just any linear separator with a large margin, so that maximizes the separation between the separator and the data points. And if I look at this algebraically, what this means is if I characterize the linear separator with the vector that's normal to it, then the inner product of this vector with all the points has to be either more or than the margin or less than minus the margin. And equivalently, we can renormalize things, and instead of talking about a unit vector, require the margin to be 1, and then what corresponds to the margin is just the norm of the vector, 1 over the norm of the vector, which means that we can, and also we maybe can't hope to get or not want to get complete separation. There might be some noise, there might be some points that we can't quite separate, and that's okay, we're just going to pay for them. And how much we're going to pay for them is just how far they are from where they're supposed to be. So for example, for this red point that's on the wrong side of the margin, we just pay this much. Okay. So what this means is that basically we can think of SVM training as a problem of finding this best separating large margin hyperplane, as a problem of, on one hand, maximizing the margin, which means minimizing the norm of W, and on the other hand, minimizing the error. And again, the error is this so-called hinge loss, which just looks at how far points are from where they're supposed to be. And the end result of all this quick story is that training a support vector machine essentially boils to solving a convex optimization problem, which is minimize some combination controlled by regularization parameter here, in this case denoted by lambda, of the norm of W and the error. Okay, so again, I presume that many of you have already seen such presentations of SVM. And so we're left with this optimization problem. How do we solve this optimization problem? So, this is just a convex optimization problem. It actually can be written as a quadratic program. And we can throw it into QP solvers. So a straightforward optimization methods for this problem based on sort of popular methods for solving quadratic programs, interior point methods, would take time that scales roughly fourth or maybe 10 to the 3.5 maybe with the size of the data set. Okay? So this is fine for solving SVMs for size of up to maybe 100 variables or so. And there's been much improvements to this. So the most popular methods probably now for dealing with the support vector machine optimization are based on decomposing the dual problems, so-called the SMO or other approaches, and they can get the runtime down to scale only quadratically with the size of the problem. So we have a quadratic increase of the problem with the size of the problem at the cost of only linear as opposed to quadratic convergence, so dependence on log accuracy as opposed to log accuracy. And more recently, there have been methods suggested, this is specifically for linear problems, which scale only linearly with the size of a problem. Okay, so all these methods look at really the problem's optimization problem. Okay, and all of them tell us that when we have more data, then we should be expecting to work more. And they just sort of try to push that down to be this, we're going to work more, but maybe not as badly. So instead of having a fourth order increase, maybe we can go down to only a linear increase with the size of data. But in any case, we study the problem here as we do for most problems in machine learning and computer science. In fact, we look at the runtime as an increasing function of the size of the data set. Okay? And my main point I'd like to make is this study seems somehow wrong. So the runtime should not increase with the amount of data. Okay, so let's look at what's going on here. So what do we use an SVM for in the first place? And we use it in order to get some predictor that will have good error when we use it in some tasks, say character recognition or whatnot. So we don't want to do character recognition. We train an SVM and then use that to do character recognition. So suppose that given 10,000 examples, you give me 10,000 examples, I can work for an hour and produce your predictor that makes 2.3% error on my character recognition task. Okay, so that's great. And now you give me, and maybe I'm happy with this 2.3% error. Okay, and now you give me 1,000,000 examples. You give me 100 times more data. Okay, so what the traditional SVM optimization approach would say is that now I'm going to crank this through my optimization solvers. They're going to scale it best linearly and more realistically quadratically with the size of the training set, which means instead of running for an hour, they're going to work for maybe a week. And after that week, okay, I will get a somewhat better prediction error. Maybe instead of getting 2.3% error, I'll get 2.9% error. But if I was happy with my 2.3% error, there's absolutely no reason for me to work for this entire week. I mean, definitely what I can do is just subsample. So take only 10,000 out of those 1,000,000 examples, throw away the other 990,000, do exactly what I did before, work for an hour, just like I did before, and get that 2.3% error. Okay? And this general argument generally applies. So when studying a machine learning problem from the perspective of how much work do I have to do in order to get some performance, and performance here is target accuracy, okay? How much work do I have to do? The amount of work should never scale up with the amount of data that I have. In fact, what we'll see is that what we can hope for and can get is it should scale down. So instead of just subsampling, I can do something more sophisticated, use those 10,000,000 examples, not throw them away, and instead of working for an hour, work for only 10 minutes and get the same 2.3% error. Okay? So what we're going to see is how to look at runtime as a decreasing function of the amount of available data, how we can use more data in order to make training take less time. Okay? But in any case, what definitely I hope I've convinced you is that you should definitely not study runtime as an increasing function of the amount of available data, because at the very least it should not increase. Okay? Now, you might be thinking, okay, I don't really buy this because maybe you really do care about that 0.01% increase in performance. Really, maybe it really is important for you to get better performance. Okay, to get better predictive accuracy, and that's fine. Okay, but then you should study how runtime increases as a function of what target accuracy you want, and that's fine. If you want more target accuracy, you're going to have to work harder, and that's fine. But you should. So if you tell me I want you to work harder, so if you tell me I'm going to take more time because I want higher target accuracy, that's fine. But if you're saying, oh no, I have a large data set, I'm going to have to work harder, that's wrong. Okay, you can also say, well, I mean, some problems are really hard. Okay? Some problems really do require to crunch for a week. I mean, you might have a problem that's so hard that really you're not going to get anywhere without crunching for a week. And that's also fine. Okay? But in that case, what you really should be studying is how runtime scales with the hardness, intrinsic hardness of your problem. So in particular, in SVM problems, in large margin problems, maybe this hardness is captured by the margin. If you have a very, very small margin, yes, it's harder to learn. And in that case, you can say, okay, if I have a small margin, I'm going to have to run for more time. So I want to look at how runtime scales, how runtime increases as the margin decreases, or the norm of W increases. But again, just saying I have more data, and because I have more data, I'm going to run for more time, or looking at the runtime dependence, which scales increasing function of n, is wrong. Okay, so we'll see this particular for SVM. So let's look back at SVM training and look at what's going on here. Okay, so we wrote SVM training as optimizing an objective, and the issue is that all the traditional runtime analysis is, and it's not only runtime analysis, also the traditional optimization methods for SVM really treat this as an optimization problem and ask to get a very accurate solution on the optimization objective. How the runtimes I showed you before say how much runtime does it take to get within epsilon of this optimization objective. But that's not really what we care about. I mean, it's true that we optimize the optimization objective, but that's not what we really want to minimize. What we really want to minimize is our true objective, which is the prediction error. We want to get low error on future examples. Okay? So why don't we just minimize this directly when we can't minimize this directly because we don't observe our future error. Okay? So, but that's what we really care about. So instead of minimizing the future error, what we actually do is minimize some surrogate for it in terms of the training error and add a regularization, and so we minimize our optimization objective, f, that's denoted here by f. But that doesn't mean that when we study runtime, we should study it in terms of how low we get f, because I don't really care to get my optimization objective really, really, really low. What I care about is getting my predictive error very, very, very low. So what we're going to do is study optimizing f in terms of how well do we do on the error. Okay? So, and in particular, we're going to look at how the computational cost of optimization, okay, as we said before, increases as a function of the desired generalization performance. So it increases not in terms of the epsilon f, in terms of how accurately I get f, but it's going to increase in terms of how low do I want to drive my error. Okay? And it's going to increase in terms of how hard the problem is, or in terms of like how small the margin is. But it's going to decrease as a function of the data set size. Okay? And let's see why we might hope to get that. And in order to do so, it'd be useful to look at the error decomposition. I'm sure many of you have already seen the standard error decomposition in machine learning. And usually in learning tasks, we talk about when we decompose the error into the approximation error. So this is the error that kind of says, okay, even if we had tons of data, okay, this is the best error that we can get with a hypothesis in our hypothesis class. Okay, so in our case, you can think of it as the best error achievable by a large margin separator. Okay? It's actually a bit trickier here since we're talking about a regularizer and not strictly limiting to hypothesis class, but we can define things appropriately. Sort of the error achievable by the population minimizer. If we had infinite data, what would be our error? Okay? So this is in some sense the unavoidable error in a sense. Okay? And on top of that, we add the estimation error. And the estimation error results from the fact that we don't have infinite data. We're only doing everything based on an estimate of the error, which is given by the training error. Okay? So this is a standard decomposition that I'm assuming many of you are familiar with. But really, this decomposition refers to this W star, which is the mathematical minimizer of the SVM objective. But we never have the mathematical minimizer of the SVM objective. After all, we run some SVM optimization, and it runs for some finite time and gives us some predictor which is finitely close to the true mathematically defined optimum. Okay? So really what we have to add here is another error, which is the optimization error. Okay? And this is the difference between the error of the mathematical optimum and the error of what our algorithm actually returns. Okay? Okay? So, and I should point out the very similar decomposition has been suggested, talked also about a year ago by Leon Boutou and Olivier Bousquet. Okay, so now, so this is error decomposition. Now let's think about what happens when I have more data. Okay, when the training size increases. So when I have more data, okay, the approximation error is the same, but the estimation error decreases, right? Because the estimation error depends on data set size. The more data I have, I can do the estimation better, and the estimation error goes down. But recall that our target here is to get some target performance, our desired 2.3% error. So if the estimation error decreases, I can, in some sense, the mathematically defined optimum is better. That means then I can do a much worse time optimizing. I don't have to optimize as well. I have so much data that I can just if I really optimized all the way, maybe I'll get lower error, but I can afford to just do a bad job optimizing. So what this means in particular is that I can maybe take less time optimizing. If I have an iterative optimization methods, and most of our optimization methods are iterative, I can run for less iterations. So that's good, and that should mean that I can run in lower runtime, which is what I want. However, with most optimization approaches, situation is a bit trickier, okay? And really, increasing data set size is a double-edged sword. On one hand, it's true, I can run for less iterations, I can do a worse job optimizing. On the other hand, each optimization iteration takes much more time, okay? So in traditional optimization approaches, each optimization iteration, I look at the entire data set and maybe do even something complicated with the entire data set. So each optimization iteration by itself scales linearly, maybe quadratically, with the amount of data. And so overall, I'm not going to win here, or at least not win much. I'm going to do less iterations, but each iteration is going to be much more expensive. Okay? So this is why we don't get this type of behavior with standard approaches, but we do get this if we move to stochastic gradient descent. Okay? So last year we presented a specific stochastic gradient descent optimization approach, which I'll present in the next slide, called PEGASOS. And the important point about PEGASOS, or any stochastic gradient descent optimizer for that matter, is that the runtime for each iteration is fixed. At each iteration we only look at a single example. Okay? So the runtime of each iteration does not increase with the number of with the sample size. Okay? So once we can optimize, we can do worse job optimizing. We need less iterations. The cost of each iteration is fixed, and we really do get a gain in runtime. Okay. So let's look at PEGASOS. Again, PEGASOS is a fairly straightforward stochastic gradient descent optimizer. What we do is at each iteration we look at one random training example from our training set. We look at our objective limited only to that example. Okay, so this is what's written here, the error in that example plus the regularization term. We calculate the gradient, or it's actually subgradient since it's not differentiable, but that's really not important. You can just think of it as calculating gradient of this function and take a step in the direction opposite the gradient with the predetermined series of step sizes that behave as roughly 1 over t, so 1 over the number of iterations. So each iteration we're taking smaller and smaller steps. So that's all. So each iteration is very, very simple. You take a random point, you calculate the gradient, which only requires looking at the example, okay, and you take a step in that direction. So the cost of each iteration just scales linearly with the representation of a single example. Okay? And the major important result here is that in order to get within epsilon of the optimum of the objective function, so again this is now an epsilon on the optimization objective, we only need 1 over lambda epsilon iteration. So number of iterations does not depend on the size of the data of the training set. Okay? Which means that and as I said before, the cost of each iteration only scales linearly with the size of each example, or even if it's sparse, it's even better. It's just the size of representation of each example, which means that the total runtime for PEGASOS to get within epsilon on the optimization objective does not increase at all with the size of the training set. It's just the dimensionality of the data, or the sparsity of the data, over lambda, which is the regularization parameter, times epsilon. Okay, so what we see here is that we have no runtime dependence on the training set size. I promised you a decreasing dependence on the training set size, and we're going to see that shortly, because remember that this is runtime dependence for an epsilon, which is the optimization epsilon. Okay, so before going on, it is important to realize here that PEGASOS is also a good method. I mean, I'm going to quickly flash a slide with some empirical results. I mean, the major point here is that PEGASOS, these are some standard large sparse SVM training benchmarks, and PEGASOS gets significantly better performance than previous methods. But this is really not the major point I want to talk about. So let's go back to comparing the actual runtimes. And if we look at the runtime of PEGASOS compared to other methods, it's actually a bit difficult to compare the runtimes, because, so now I'm again talking about this traditional optimization runtime comparison. It's a bit tricky to compare these runtimes, because on one hand, PEGASOS doesn't have a scaling at all on the training set size, whereas other methods have a linear or even quadratic or worse scaling. On the other hand, PEGASOS has a very bad dependence on optimization accuracy on this epsilon, which is how close do I get to the optimization objective. Whereas other methods have only logarithmic or maybe even double logarithmic behavior. And also there's this like lambda, the optimization trade-off parameter kind of comes into the runtime. And I mean, I don't know exactly how to look at that. I mean, what is this better or is this worse? I don't know. Okay? And this is, in a sense, from my perspective, because as we said before, this is really runtime analysis in terms of the wrong parameters. These are not parameters of the learning problem. Okay? The optimization accuracy is sort of parameter of the optimization problem, not of the learning problem. It's not something I really care about. I care about what error I'm going to get. Okay? This optimization trade-off lambda is some mechanism I use in order to balance the margin and the error, but it doesn't really tell me something about how hard or easy my problem is. Okay? So what we're going to do before, so I'm still going to show you how we get a decreasing dependence on runtime, but before we do that, let's just try to understand these runtimes, and we'll see that that's going to be helpful for us also for seeing the decreasing behavior. And we'll try to understand them, as we promised before, in terms of the parameters of the learning problem, in terms of the desired generalization performance, the desired error, okay? Not this optimization epsilon, but the actual error I'm going to get on future predictions, and in terms of the hardness of the problem, the inherent hardness of the problem, how big a margin is it, how noisy is it, okay? And in order to do that, okay, we're going to look at the following situation. So suppose there is some large margin predictor. Okay, I don't know it. Okay, I want to learn. Okay, but we're assuming that it is possible to separate the data with large margin and low error. In particular, there is some predictor W naught. It has low norm, corresponding to a large margin, and small error. And what we're going to ask is, what's the runtime in order to get error, which is almost as predictor W with error, which is almost as good as this Oracle predictor that we know exists, but of course we don't know it. Okay? And what we're going to look at is we're going to study the runtime required to find such a W as a function of this epsilon and the margin. Okay? Now again, this epsilon is very different than optimization epsilon. This epsilon actually talks about the quantity that really interests me, the predictive error. Okay? Okay. So in order to do that, I'm going to go fairly quickly through this analysis. We can decompose our the error of W. This is roughly the composition that we had before to the error. So we're sort of comparing it to the error of W naught. So we're decomposing it to the error of W naught plus, and then we're sort of adding and subtracting the expected SVM objectives. What this boils down to is we have the error of W naught, another term here which is roughly the approximation error, which depends on the norm of W naught. Okay? Plus these two terms which replace the difference in the expected SVM objectives, which is the difference in the actual SVM objectives of the two predictors, and the term that measures how quickly the actual SVM objective approaches its expectation. Okay? So roughly speaking, this is the approximation error. This is what's going on here. This is the optimization error, okay? And this is the estimation error. Okay? But the details here are not so important. Okay, so what's important is then I can bound. Okay, I can bound this term here. So what is this term here? This term here asks by how much bigger is the SVM objective on W than the SVM objective on W naught. Okay. Now I know that if I actually optimize my SVM objective, then I will find a W that absolutely minimizes the SVM objective. So this term will never be positive. Okay. However, I don't completely optimize it. I only optimize it to within some epsilon. Okay. And so I can bound this term in terms of my optimization accuracy. Okay? So this epsilon is the epsilon that measures how close I am to the optimum of f. Okay? And now, recall that what we wanted is we wanted to get a predictor W that has overall small error. In particular, its error is equal to the error of W naught plus epsilon. Okay? So in order to get that, okay, we definitely have to bound each of these three terms by something which is order epsilon. Okay? So because we want their sum to be order epsilon. And what this tells us is now we can go back and from each of these three inequalities extract bounds on what does lambda have to be, okay? What does epsilon accuracy have to be, what's optimization accuracy have to be, and how big a data set size we need. Okay? And what we see is that in order to get such a predictor that we want, we need lambda to scale roughly as epsilon over the epsilon times the margin square, the optimization accuracy to be roughly the same order of our epsilon that we wanted here, and the data set size to scale in a familiar way, grow with the margin squared and the target error squared. Okay, so what we can do with this now is go back to our traditional runtime analysis, and our traditional runtime analysis was in terms of the data set size that we use and this optimization accuracy and this lambda, and plug in these requirements on lambda, the optimization accuracy, and the dataset size into our traditional runtime analysis. Okay? And we do that, we get in runtime analysis, which now is in terms of the norm of W squared, which you can think of as 1 over the margin. Okay, so the larger the norm of W is, the harder the problem is, the smaller the margin. And an epsilon, which is our epsilon on the error. How close are we to the optimal predictive error that we can get? Okay, so we got what we wanted, which is a runtime analysis in terms of the actual parameters of the learning problem. How hard is the learning problem, and how accurate a solution do we want to the learning problem? Okay, and what we can see from this analysis, okay, is in fact that PEGASOS has a much better runtime guarantee than other methods. It only scales quadratically, both on the margin and the desired error, whereas other methods have a 4th order or even 7th order scaling. Okay? So what I hope I convinced you so far is only, well, maybe I hope we convinced that this is maybe a better way to look at the runtime of SVM optimization, and provides us a better way to sort of compare different methods in terms of how well do they actually deliver to us what we want, which is a good predictor. Okay? And that looking at this way, PEGASOS actually does have a significant benefit over other methods, which explains our empirical results also. Okay, but notice that in doing all this analysis, I got to set the data set. So I chose whichever data set I wanted. Okay? What does this mean? This means that this actually, you can think of it as corresponding to the situation in which I have unlimited data. I can always ask you for more data, or I have like an infinite data source, and I can choose the optimal data set size to work with. Okay? So I choose a data set size that exactly suits me and gives me the error that I want. Okay? Now, so you can think of this as sort of a data-laden analysis. Okay? This is the absolute minimum runtime that you would need if you would have access to unlimited data, so that you can choose to work with however data you want. But in reality, we usually don't work in this data-laden regime. We have just some limited data set, and that's what we have to work with. Okay? So now let's go back and look at how runtime scales with the amount of data. Okay? So let's go back here and look at the scale of runtime as a function of training set size. And what this data-laden analysis tells us is that if I have enough data, this is sort of the minimum I can hope for. The minimum runtime, if I have on however much data I want. Now, of course, it's not that with any amount of data I can get this runtime. In particular, remember that this analysis is runtime to get a fixed predictive accuracy, to get 1% error, okay? 1% predictive error. So there's some limit on how much training data I definitely need. And this limit comes from the standard statistical analysis relating sample size and predictive accuracy. I mean, in order to get my 1% error, I definitely need some minimal number of examples, 100,000 examples or whatnot. Okay? If I have less examples than this, doesn't matter how much I work, I'm never going to be able to find a good predictor. Just statistically, it's impossible. Okay? So this is sort of my statistical limit. It measures just how much samples I need. I know that if I'm on the right of this blue line, on the right of the statistical limit, if I worked hard enough, if I really optimize that SVM objective all the way down, I'll get the error that I want. But it's still very difficult to do that, because now, if I'm just to the right of this, I really have to optimize my optimization objective really all the way down and do a really good job optimizing, which is going to take me a lot of time. Okay? What happens is, as I cross this, and I have more and more data, I can do a worse job optimizing and gradually decrease this runtime. And we can analyze exactly, looking at the error decomposition, this point is exactly the point in which the approximation error and estimation error themselves already account for all the error I'm willing to tolerate. So there's absolutely no room for optimization error. I have to drive the optimization error to 0. Right? As my data set size increases beyond this point, okay, there's now room for messing around. Okay? There's room for doing a bad job optimizing and taking less time. Okay, so in the case at least of PEGASOS, we can do this analysis exactly, and we just go essentially taking the calculation from before and putting in the actual expression for the optimization error of PEGASOS after a fixed number of iterations, and get an expression for the runtime when we have only a limited amount of data. So it's square root of n data. Okay? And what we now get is an expression which behaves in the way we wanted it to behave, or the way that makes sense that the runtime would behave. Okay? So it increases with when epsilon is small. Okay, when my target error, when I want small predictive error, I need to run for longer. Okay, we're fine with that. It increases when I have smaller margin. Okay, so the smaller the margin that I know I have there, it's going to take me more time. We're fine with that. We know that's going to happen. But it decreases with the size of the data set. Okay, so the larger data set I have to actually run for less time. And this function, so this is a theoretically derived bound, and it's shown over here in this decreasing curve, which bridges between this statistical limit, okay, down to the minimal runtime that we know that we have, the data laden limit. Okay. Okay. So this is all just an analysis of an upper bound. Okay. So this gives me an upper bound on the runtime, and the question is, does this actually hold in practice? And we actually observe this behavior empirically. So this is this plot shows what's the runtime training on the Reuters dataset. So this is a fairly large standard benchmark datasets for SVM training. And we try to get an error of, set the target error level to 5.25, which is a bit about less than less than 1 promille above the best you can actually get in this dataset. Okay? And we look at the runtime to get this accuracy if we only train in a subset of the Reuters dataset. And what we in fact see is that, as predicted by a theory, when we have more data, the runtime actually decreases. Okay? And you need, at least for this specific example, we need about to double the amount. So past the point that you have enough data to get the 5.25% error, past the statistical limit, you need about twice as many. That's all. Okay, so this example, it's only twice as many. The examples, you need as many as 10 times as many examples in order to be able to reduce the runtime. So in order to be able to get to the sort of asymptotic runtime. In particular, when you have about twice as many examples, we reduce the time here by about 7-fold. So you have twice as much data. It means you have to run for 7 times less time. Okay, in this particular example. Okay, so we see here that we get this behavior of decreasing runtime as the data size increases, and this is both the behavior that kind of argues the behavior you would expect, and this is, as far as we know, the first presentation. We see it both a theoretical analysis of how and why and what we would get that, and an empirical study actually showing that we actually get this in practice. And it's important to again note that we're getting a decrease on the best method for this data set. Okay, now I want to go back here actually and now correct something I said, because the situation there is a bit more subtle than what I said. What actually happens as we increase the training set size, not only do we increase the optimization error, but actually we also increase the approximation error. Okay? So when we have more and more data, the estimation error decreases. So we could have just kept the approximation error fixed and increased the optimization error. It's actually better to also increase the approximation error. What do I mean by increase the approximation error? So for a second, ignore what's written here. At least intuitively, the approximation error measures the error on the fixed hypothesis class. If I now, instead of considering that hypothesis class, I'm going to consider a more limited hypothesis class, a smaller hypothesis class, it means that I'm making my life harder. I have less flexibility in choosing a predictor, which means that I'm going to have a higher approximation error. I'm going to do a worse job with approximating my target. But the hypothesis class is smaller, which maybe means that it's going to be easier for me to run on it. It's going to be lower runtime, which is what I want to get here. So this is what's going on here. Here the situation is more subtle. What controls the approximation error is lambda. Okay, when lambda is very large, it means that I'm very restrictive in what predictors I can choose, and I have large approximation error. Okay, when lambda is very small, then it means I'm very unrestricted and I have high approximation error. Okay, low approximation error. Okay, so in particular, what happens here is as we increase the training set size, okay, we can increase lambda. So this is, for those of you that might be familiar with results in SVM consistency or just generally with SVM training, you're used to thinking of decreasing lambda as the runtime increases, and the reason we decrease lambda is in order to decrease the approximation error, because that's what we do if we want to drive the error to 0. But here what we care about is driving the runtime to be small, okay, within our budget of what training error we allow. Okay? And the best way to do that is actually to increase lambda, okay, which means that we're doing more regularization but taking less runtime. Okay. Okay, so back to the main story here. Okay, so I have about 20 more minutes or so. Okay, so I just want to, before going on, we said that for stochastic gradient descent, for PEGASOS, we get this decreasing behavior. We can also ask what happens for other methods. So we can repeat the same analysis for dual decomposition methods such as SMO and for SVM perf. And what we see in those cases is a function of runtime. When we increase a function of data set size. If I increase the size of the amount of data which I run the algorithm on, okay, Well, at first I get a very sharp decrease when really I'm allowing no optimization error to allowing a bit of optimization error. But then very quickly the runtime increases. In particular, there's some optimal data set size, which going beyond that optimal data set size is only going to do me harm. Okay, so running the data on larger and larger data actually, running the optimizer on larger and larger data actually takes more time, which is maybe not surprising. This matches the standard analysis of these methods, and it's kind of what we're used to, that if we use more data, then it takes more time. But again, this type of behavior is in some sense wrong. The same situation also happens in SVM perf, which is sort of a cutting plane method, not so important, slightly not quite as bad. And we can also see these behaviors empirically. So here we're comparing, we're seeing these two methods. For the dual decomposition methods, SMO here implemented with SVM light algorithm, we see a sharp increase. It's very difficult to detect this initial decrease. And for methods like SVM, specifically for SVM perf, for cutting plane methods, which are sort of have a much more nicer dependence on data set size, at least according to the traditional approach, we do see an initial decrease, but then runtime starts increasing. Again, this is opposed to stochastic gradient descent, where you just continue going down. Okay, okay, so skip this. Okay, so let's summarize what's going on here. And first, I have to make a confession. And I really talked all the time about SVM optimization. Everything I said about PEGASOS holds only for so-called linear kernels. So for the problem is, as I presented in the first slide, which is we're explicitly given data, we're explicitly given features in RD. Okay? We're explicitly given our feature vectors, and then we get the performance guarantees that we get, and everything is fine. Okay? You can run PEGASOS. You can run stochastic gradient descent also when you use actual kernels, nonlinear kernels, in a more familiar application of SVMs, but then things become a bit trickier. So you do, in particular, although you can run PEGASOS and get the same guarantees on number of iteration, the cost of each iteration does increase with the amount of data, because you have to represent everything in terms of the support. So in terms of the support vectors, number of support vectors can increase, and you get into trouble. So one thing that will definitely be very interesting is to get the same type of behavior for true kernelized SVM. We're not yet able to do that, although I believe it is possible. And the other thing is, the decrease that we saw here in the runtime is really a result of the fact that we can increase the optimization error and maybe also increase a bit the approximation error. It's playing on this error decomposition, and there's a limit on how much you can gain from that. In particular, at least our theoretical analysis is almost tight. You cannot, without assuming anything else, you cannot hope to get much better decrease in runtime beyond what we're getting, at least theoretically. Okay? And it'll be fairly interesting, and I think very possible, to try to leverage this excess information more directly. So if you really have tons and tons of data, that the answer is just sort of in your face. I mean, you should not have to run. It should really help you much more significantly to reduce runtime costs, and it might be possible to do so empirically, and maybe also have theoretical analysis that are based on much sort of more complicated assumptions. So our theoretical analysis here is only based on assuming that there is a large margin predictor. Maybe if you assume a more detailed oracle assumption, assume something about how that large margin predictor looks like, or that you have a family of large margin predictors, it might be possible to get even better decreases in the runtime and more directly leverage the excess information. But going beyond SVMs, the basic story that I told here is valid for essentially any learning method, and not only SVMs. If you have more data, runtime should not increase, and in fact, it should be possible to decrease runtime when you have more data. And I'm looking forward to seeing optimization approaches for other methods, both studied in this way as a decreasing function of runtime, or at least as a function of the true parameters of the problem, and not of the optimization problem. And hopefully doing that will also bring up optimization approaches that actually have a more that actually behave this way and are more appropriate for learning. Okay, so this sums up the first half of the talk, which is about SVM optimization. What I'm going to do now is switch to something that will seem like a completely different topic, but hopefully by the end you'll see that it's not actually a completely different topic, and that's looking at the computational hardness of clustering. Okay. So what we saw in the first half of the talk is how, if you look at SVM is a problem that's always in a sense easy. It's a convex optimization problem. We can also solve it. The only question is, do we take a day, or do we take an hour? Or it's just a matter of how we scale in the parameters. Okay? Looking at clustering, and here, just to make things very simple, I'm talking about the simpler form of clustering. I have data that's generated from sort of a few Gaussian clouds, and what I want to do is reconstruct that separation into those clouds, into those Gaussians. Okay? So if you look at this problem, you can do this by maximizing the likelihood of the Gaussian model. And this problem is, it's not too difficult to show that it's hard in the worst case, okay? Which means that I have some inputs in which I can never really maximize the likelihood. If you prefer to think of it in terms of the k-means objective, this is very similar to k-means clustering. Minimizing the k-means objective is NP hard. You cannot have an algorithm that for any input data minimizes the k-means objective. But this statement is almost meaningless because those instances in which you can actually prove that this is hard, the instances you get in those reduction, are these instances in which you don't really have any clustering. They're just like a bunch of points scattered in a very specific way, in which there's no good clustering. Sure, there's one clustering that has a slightly less bad objective than all the other clustering, and finding that clustering with a slightly not quite as bad objective is hard, but who cares about that? It's not actually going to give us an actual clustering. These situations don't actually correspond to a situation in which I have some clusterings and actually want to reconstruct them. Okay? So, on the other hand, there are results that say that actually, if you do have a very distinct clustering, and clusters are very, very well separated, okay, then it's actually very easy well, not sure very easy, but then we actually do have polynomial time algorithms to reconstruct the clustering. Okay? So those guarantees, and this is a long series of papers starting with the work by Sanjay Dasgupta in 1999 and leading on to progressive improvements handling more complicated situations and slightly reducing also the required amount of data. But really all these results require the clusters to be extremely well separated and requires to have lots and lots and lots of data. Okay? More maybe importantly, the practical experience has been that if the clusters are even just reasonably distinct, you don't have to be very well separated, and you have enough data, just run EM or your favorite local search method and it'll find the clustering. Okay? And this really, so this is, again, if there really is a distinct clustering and if there's a lot of data. Now, if there isn't a distinct clustering, or if there's too little data to identify the distinct clustering, it's not really interesting to cluster. If I have too little data, the problem is not a computational problem. The problem is a statistical problem. I cannot reconstruct the clustering no matter what I do. Okay? So if this reason, if I have too little data, I can't do anything anyway. And if I have a lot of data, then it's computationally easy. So this kind of leads a general saying that I think many people subscribe to, that clustering really isn't a hard problem. Either it's easy, I have lots of data, I can just use EM and find it, or if that doesn't work, it's probably not interesting. Okay? There's probably no clustering there to find in the first place. Okay? And what we're going to check is whether this saying is correct or not. In particular, we're going to say that this is actually not the case. Okay? So let's look at the situation in terms of sort of cartoons of the likelihood. So what that's saying, revisit the situations that we described in the previous slide here. So if I have a lot of data, and this is, you can think of it as a cartoon of the likelihood surface. I have lots of data. The answer is just there's a huge peak close to the correct model. It's very easy to see from far away. It's very distinct. It's very easy to find. Computationally, it's easy. If I don't have enough data, then it's true that maybe around the correct model there's which one it is here. There's a peak, but there's also lots and lots of other peaks of the likelihood, and various other models that have nothing to do with the correct model also have high likelihood. And statistically, it's just impossible to discern between the correct model and the models that aren't correct. Okay? And what we are going to claim is that there's actually an intermediate regime, okay, where there is just enough data so that statistically the solution, the correct model is identifiable. Okay? The peak at the correct model is higher than all the other peaks, but computationally it's hard to find. It's not distinct enough to make the problem computationally easy. In particular, we're going to look at the informational limit of clustering. How much data do you need for the clustering problem to be informationally possible, disregarding computation? Okay, so this is similar to the statistical limit that we had before, and this computational limit, which is how much data you need in order for the problem to be computationally tractable. Okay? And I wish I could give you an analytic analysis of these two limits and prove to you where they are. I can't do that. What we did instead was we did a very detailed empirical study. I'm not going to have time to go into the details of the empirical study. You can appears in our ICML paper from 2 years ago from ICML 2006, or you can ask me about that later. Essentially, what we did is an empirical study trying to quantitatively evaluate these two limits. Okay? So what we have is several million results that look like this. So what we see here is a function of data set size. We see the error of the clustering error, how close are we to the correct clustering. So this is all in simulated data, so I know what the correct clustering here, of the maximum likelihood solution, or what seems to be the maximum likelihood solution, and of what we get with local search. And what we can see here is that we can identify two fairly distinct phase transitions. We have the informational limit, so this is where where the maximum likelihood starts being meaningless. If we have less data than this informational limit, then even if I can find the maximum likelihood model, it just has random error. I mean, it has nothing to do with the correct model. Beyond this point, the maximum likelihood model is good. Okay? It slightly becomes a bit better. And what we can see is if we have enough data, okay, if we have more in this case than about 4,000 examples, then just local search, EM, and this is actually EM initialized with some PCA, but it's still essentially just very simple methods, do find the correct model. So the problem is computationally easy. Okay? But there's a very wide regime between them. Okay? In this case, about a threefold increase in the amount of data. So I need about 3 times as much data for the problem to become easy. And then in all this regime, if I have between about 1,200 and 4,000 examples, the problem is actually interesting. I mean, if I had infinite computational resources, I could actually get a meaningful clustering. The problem is computationally, is sort of statistically interesting, but computationally appears to be hard. We don't EM fails, and we don't have any other methods to reconstruct the correct clustering. Okay, how does this relate to what we talked about before? So now, if we look at the runtime required to find the correct clustering as a function of data set size, we can have a similar plot to before. It looks a bit different. So we have this information limit that we had before. If we had less than this much data, we're lost. It doesn't matter what we do. I mean, the problem is statistically hard. Once we cross that, the problem becomes statistically possible, but at the cost of very difficult computation. In particular, in this case, it's possible if we enumerate over all possible clustering. So you have exponential amount of computation. Okay? And this runtime, if you can think of it as a decreasing runtime, where the decrease is not a gradual decrease where we had before, but it just a drop where at some point we can start using methods that are much more efficient, polynomial time methods, just local search methods, and the problem starts becoming tractable. So we again see here a decrease in runtime as the dataset size increases, but in this case this is not a gradual decrease as we had before, but a drop. So we have drop from exponential runtime dropping, so the problem becomes essentially dropping from being intractable to being tractable. Okay? And I'll very quickly just I mean, we can actually study the width of this. So this is what I call the cost of tractability. How much more data do we need for the problem to become tractable? What's going on here? We can study it. So I'm not going to go too much into the details. Generally, you can see here what the information limit and computational limit are as a function of the dimensionality and as the function of the number of clusters. And in both cases, you can see a linear increase. So both of them increase linearly with dimensionality number of clusters, which means that really the issue here is what's the data set size compared to dimensionality number of clusters. And so we can look at this plot, which plots the sample size per dimension per number of clusters required for reconstruction as a function of the separation between clusters. Okay, so of course, the more separation we have, the less data we need. Okay, the problem is easier. But more interestingly, what we see is this is the informational limit, this is the computational limit, that this gap, so this cost of tractability, how much more data do we need to solve the problem tractably, actually increases when we have a larger sample size. Okay? So this is a bit, maybe at first thought counterintuitive and opposite to all the theoretical results that say if we have a large separation, then things computationally are easy. Actually, what we're saying here is the opposite. Actually, when we have large separation, in absolute numbers we need less samples, okay? But the gap is much bigger, okay? If we have more separation, then actually, in a sense, the computational aspect of the problem becomes harder relative to the statistical aspect of the problem. Okay, I'm not going to spend too much time on that. This is what I said before, and let's sum up. So I hope that in both parts of the talk, and now maybe you see the connection between both parts of this talk, we saw this relationship between data and computation. And the standard view of the relationship between data and computation in computer science and in traditional study of machine learning is that if we have more data, I have to do more computation. Okay? And this is reflected both in the way we study algorithms. Traditional notions of complexity look at how badly does the runtime scale up when I have more data. Does it go up only quadratically, or does it go up exponentially? Okay? But it's definitely how much does it go up when I have more data. Unfortunately, also in machine learning, this is often the way we think about problems. We say, oh my God, I have 10 million examples. How will I ever be able to crunch that? And this is we are expecting computation to increase when we have more data. And really, definitely in machine learning, this relationship is reversed. The more data we have, the better we are. We should be happy that we have more data, not sad that we have more data. We have more data. It should mean that we should be able to do less work. Okay, and we're using data as a replacement in a sense for doing work, which really means that we should look at study runtime not as an increasing function of the data, but as a decreasing function of the available data, and instead as an increasing function of the true parameters of the machine learning problem, of how hard the problem is to separate, for example, in terms of separation between clusters or margin or any other parameter that really measures the hardness of the problem, or in terms of how good we want the solution, in terms of the desired error. Okay, and sort of this. And what we saw here is we saw. Okay, sorry. Maybe before. This is an important point. Okay, so I talked about SVM and clustering, and I want to go back a bit to the clustering. So I talked here about clustering, but really this type of behavior, this phase transition type of behavior, seems to appear in many other problems. Clustering is a problem that I studied the most, as far as a very detailed empirical study. I do want to point out several other problems. Again, we see this transition from the problem being intractable when we have only limited amount of data to being tractable when we have tons of data. So this happens for some kind of learning structure of dependency networks. We know the problem is hard in the worst case, but seems to be easy when you have tons and tons of data, so much data that we can actually measure mutual informations very precisely. The situation here is not completely resolved yet, but I'm pretty sure that it can be shown, hopefully will be shown by somebody, that this actually is easy in every case when you have enough data. Graph partitioning, which is similar to clustering, and also sort of problems like solving linear equations, discrete linear equations, or planted SAT problems. And again, the problems are hard in the worst case, but it seems that we have tons and tons of data. The problems have become easy. And the interesting here to study is how does the problem go from being hard to easy, and characterizing what's this width of the hard region, what's the cost of tractability, and establishing that there is even just a hard component to it. Okay, but so going back here, so what we see is in many problems, both continuous problems such as SVM and combinatorial problems such as clustering that we saw in many other problems, the correct way to look at the problem is to study how computation goes down with more data. And this is something that unfortunately we don't have very good understanding of. We have a very good understanding of how error goes down when we have more data. So there's decades of research in statistics, but also in statistical learning theory, that tells us how much data we need to get a certain error. How does the error decrease when we have more data? But especially in today's world, where we often have access to massive amounts of data, it can often be useful to use the excess data not in order to get a 0.001 decrease in error, but rather to get a significant decrease in runtime. And that's something that's very interesting to study, both from an empirical perspective and a theoretical perspective. And just want to again remind you that specifically for SVMs with linear kernels, we sort of solved this in terms of by showing that stochastic gradient descent actually has this behavior. And I'm looking forward to seeing methods with such behavior also for other continuous problems such as SVMs, in which we get, sort of, again, remind you this behavior on the left, and understanding combinatorial problems, why exactly characterizing the behavior that seems to happen in many combinatorial problems. Okay, so I think that's it.
Questions?
So one thing that was sort of missing was a characterization of the meaningful minimum error. So in a lot of problems, why we care about more data is because that actual 0.001 matters, because we're talking about a class that's present 1% of the time, or 1% of 1%. Okay. And subsampling the data means throwing it out. In a multi-class problem, if you have a power law in the class representation, it means that subsampling, you're throwing out the majority of all your classes. And yeah, you're getting the big class, but who cares? That's basic anyway.
So, I mean, the study that we present in particular, if I go back to the theoretical analysis, for example, does definitely include that error term in it. So that error terms appear here, and if you really care about that 0.001, it means that you really need to drive this lower, and you're going to pay for that in terms of runtime. Okay? So this is definitely consistent with the study. Okay? There is, nevertheless, I mean, so it may mean that you need a smaller error, but for whatever error that you are willing to tolerate, okay, for that error, if you have more data, the runtime should decrease. Now, if you're talking specifically about a problem where you say, okay, my expected error over all examples doesn't really measure what I really want because it's dominated by the big class, and what I really want to do is find the rare things. Then, in that case, what you should do is look at a different error measure, the error measure that is the error measure that you care about. For example, something in terms of precision recall or whatever other measure that you have that you measure how much that really captures those rare things, okay? And do a similar study for that error measure. So the study I presented here is for using SVMs for a standard prediction task where what I care about is the expected error. Okay? So the basic idea, the basic concept is still valid. I mean, even if whatever error measure that you care about, okay, error measure, so precision recall error measure, you would still expect to get such behavior. The specifics of the math that I showed would not apply to your setting. I mean, they're specific for this SVM setting. Though again, I believe you can sit in it enough, you'll be able to derive the math that's specific to your setting. Does this answer the question?
I guess what I'm saying is that I'd rather have a characterization of how much error should I care about, because I'm skeptical of deriving it for things like other measures, because I continuously see theoreticians work on error instead of these other measures, because presumably that's what's easy to prove, or what's actually used in practice are these other measures.
Okay.
Some insight in sort of how do we get a characterization of how much error should I care about given things like class presence or other variables, because that's why usually you retain all the
yes. So my answer to that would be that is not how much error you should aim for in that case, but in that case just looking at the error is the wrong thing. I mean, you should be looking at other measures, and I think it's true that maybe if you look at theoretical work, it's probably is true that it's sort of gives an overemphasis to very straightforward error measures because they're much easier to work with. Nevertheless, there is theoretical work also on things like precision recall and other measures that do pay attention to rare events. I'm not specifically familiar with things to point out to you, but again, my basic answer is that you should study performance in terms of the error measure that you do actually care about and is suited to your particular need or application, rather than think about what very, very, very small error is going to guarantee what I want.
So here's another correct. I want to sort of represent what you're saying in a different way, and you can correct me if I'm wrong. So would it be true to say that essentially the intuition is that if you have a large data set and you're sampling, which is what PEGASOS does, right? And you're going to get like a really, say, unbiased sample of the real world, because if you actually have enough, large amounts of data set, you actually have the real world out there that you're sampling from. Whereas if you don't do sampling, if you just take everything into account, you're just going to pay in runtime because you have to go for everything. So essentially, think of it like when you have a small data set, it's like you have potentially a biased sample from the world. Whereas if you have a large data set which you sample from, you probably get closer to an unbiased sample.
So definitely, at least the second thing that we said exactly characterizes why PEGASOS gets this gain. I mean, PEGASOS being a stochastic gradient method, and this is all stochastic methods, what we do is we have a big bucket of examples, and each iteration we pick one example from our bucket, look in it, do our little tiny computation, and put it back, and then pick another example and repeat. And so the best thing we could hope for is instead of having a bucket of examples, we just get fresh new samples from the world all the time. That's not the situation. What we're giving in a training set, we're giving a fixed bucket. The bigger that bucket is, the better it sort of represents the world. And so the better, we're not going to pay for it in terms of runtime. The runtime is going to be the same, but other things are going to be better. And so we're going to get better samples each iteration and be able to kind of do a more effective step at each iteration. So that's definitely true. Comparing that to batch methods is a bit trickier. So definitely generally stochastic methods seem to be have dominant performance in machine learning type applications because, in a sense, we don't care about. So it's very difficult to get very small optimization accuracy with stochastic methods. Okay, the convergence rate. If I was giving this talk in a optimization conference, I would be kicked out of the room. And I mean, this was. I don't know if there are any OR people here, or if they're like they feel like, oh, what is he doing? Because really, if we go to our runtime guarantees, I mean, getting a performance guarantee which scales as 1 over the optimization error, and this is horrible. Okay? And so, from a pure optimization perspective, stochastic methods are problematic. And the reason I think why stochastic methods are better than batch methods, and I do think this is a general principle that stochastic methods are preferable to batch methods in a learning setting, is exactly because we don't really care about getting very small optimization error. Okay? There's no point in getting optimization error which is much smaller than the inherent error you anyway have because of estimation error or because of approximation error. Okay? And so I'm not sure this is I think a more subtle issue because in some cases batch methods are better. Okay? And it's not so clear to say. In learning settings, this type of analysis shows us that stochastic methods dominate. Batch methods, there's also a nice analysis, again, by Leon Boutou from a year ago that was for unregularized linear prediction in low dimensions. It also had similar, to look at the data-laden case there, and also got similar results showing that stochastic methods seem to be particularly appropriate for machine learning applications because of that property. Yes?
How do you think about the noises in data?
I'm sorry? Noisy data?
Yeah, if you have incorrect labels.
Okay, so that would come out, note that we're saying that we have some predictor that has large margin, but also has some error. Okay, so we are allowing there to be noise in the system. Because of course, the more noise that you have in your labels, then the more noise you're going to have also in your answers.
So regarding kernelizing this method, I don't see how you can get rid of n because no parameterization is.
You can't. That's my problem. So we can kernelize, as I said, we can kernelize PEGASOS, but we don't get the same runtime guarantees because we do get a runtime dependence on n.
So either you work in alternative parameterization if there is any, or
yeah.
What's your take on it? I mean, do you have?
My take on it is that you should limit the number of support vectors you have. So you should kernelize it. If you just kernelize in a straightforward way, you're going to have linear dependence on n. But you should kernelize, but be very reluctant to add new support vectors. I don't know how to do this. Okay. Yeah. No, I'm going to say I don't have an answer here for the kernelized case. A straightforward kernelization here would have a runtime dependence on n. I strongly believe that it is possible to come up with a natural method that would have a similar scaling even for the kernelized case, and I don't know how to do that. If you have a good idea how to do that, okay.
So some of the problems that I work on are like based on Bayesian inference.
Mm-hmm.
And the intuition there is as you have more data, your posterior distribution tends to be normal because of law of large numbers. And that kind of fits in with this intuition that the problem is easier there. Right? Since because if posterior is a normal distribution, finding the mode is much easier.
Well, the posterior, I'm not sure. Okay, maybe we can talk about this offline. I'm not sure I agree to that because, for example, in all these problems you have multiple modes, and it's only normal around each mode, and the real problem is finding the mode. But the real problem there is finding them. But usually that's the hard part. I mean, the combinatorial aspect of the problem, finding the correct mode, is the hard problem. So,
so that's the exchangeability part. But, like, say the Bayesian counterparts to SVM, the Gaussian process classification, yes, for instance, right?
Oh, you're talking about the convex problems?
Yeah.
Okay.
Not convex problems, but I mean these are Gaussian process classifications, right? The most successful approaches are the ones that approximate the posterior as a Gaussian. Okay. So you can actually prove that the posterior is increasingly going to get Gaussian as you see more and more observations. So again, I mean I'm saying that kind of fits in from a Bayesian perspective to this analysis rather than from an optimization perspective, where as you see more and more data, your posterior is easier to estimate, but easier to approximate.
I'm not sure. I mean, we should maybe talk about this. Other questions?
Let's thank the speaker again.
Mhm.